title is fairly long-winded. We call it internally the River Pumps Project. This pumping station supplies water to Sappi Tugela's mill. It's the lifeblood of the mill. So every time we were messing around with this plant, it was obviously very risky and a lot of pressure on us to make sure we didn't bring the mill down. I'm going to go through the project beginnings, how it started, the investigation, the process. I'm going to try and explain how the plant works. It's not that complicated, and I think it's a bit more interesting if you understand the plant, and then the detailed investigations procedures, and then our findings and solution. The project started in October 2006. We were asked to look at the high-lift pump station at Sappi's Tugela mill, a river pump plant. The mill at that stage was thinking about upgrading the impeller on one of their high-lift pumps. So that's where we started off, and we walked into this plant with sort of that idea in mind. One person suggested, and at that stage, just to go back a bit, Eskom, we had all this sort of load shedding issues floating around, and Eskom was funding load shifting projects. Now, for those of you who don't know, load shifting is when you switch off a plant during peak periods of the day so that you can counteract the peak on the grid. That's because of everyone going home and switching on their stoves and geysers, and Eskom has this peak that they struggle to handle. So the idea is to switch off plants during that period of the day and counteract that grid, that peak. And Eskom was funding those type of projects quite heavily and pushing for them. But anyway, we proceeded. We went to meet the personnel in the plant. First thing I got told, there's no ways you can stop this plant to run 24 hours a day. Flat out. The water quality changes overnight. There's no ways you don't know what's going to happen. The turbidity suddenly can go as high as 10,000 NTU. You can't process it. We can't keep up with the mill. We struggle. You can't stop the plant. We proceeded anyway. Started gathering production data, power consumption data, equipment data, capacities. We even did a GPS survey of the plant because it's quite a big, or physically it's laid out over a fair area, and there's no detailed drawings showing you the heights of the various pieces of equipment. So we did a GPS survey to figure out static heads, pumping heads. This is the original plant configuration. Pump from the river, about 3 parallel pumps up to a header tank that goes down by gravity to some cyclones, separate out the heavy waste that comes from the river. Obviously there's a lot of stone and grit and stuff that has to be removed. The accepts from that go then into a transfer tank, and then parallel to that there was another what they call grit chamber. And then they process the water through the rest of the plant. They go through basically sedimentation processes where in principle you're just allowing the dirt to settle out and the accepts overflow and proceed forward through the process, and then it gets pumped up to the mill. Looking at the static heads, you can see we're starting at sort of a 13.9 meters, that's above sea level, 40 meters and up to 100 meters up above the plant, up at the mill. In picture form, this is suction from the river. Those are the 3 pumps drawing from the river up to this chamber on top where that's like a header tank. These are the cyclones. There's what their own homegrown what they call the centripetal grit chamber. They made this themselves because they didn't feel like buying it from anyone. So they designed that themselves. There's the transfer tank, 3 pumps, original pumps in parallel. Here's the sedimentation basins. That's got the highest throughput of all the various processes, sedimentation processes they've got there. That's at plant level. There's 2 of those. These are what they call the Moore units or clarifiers. What historically happened with this plant is they started off with the sedimentation basins, then they needed a bit more capacity, so they added something else, and they added something else, and every time they were adding something else, the technology had changed, so we were adding a different piece of equipment. And then that's the A reservoir or clarifier, which is a sort of typical, more modern design clarifier. And then it overflowed from the clarifier to what they call the B reservoir, which was their way. I think when they did the original project, they put in another big reservoir which could be converted to a clarifier in the future. And that B reservoir was a key part of this whole project, and we were quite lucky that it was there. From all those sedimentation processes, all the clean water flows into their balancing tanks, and then it's pumped by 5, we're now over here, it's pumped by these 5 parallel pumps up to the mill reservoir. This pumping section draws about 1.48 or 1.5 megawatts of power. the whole plant runs at about 2.2 megawatts. And one of the really nice things about this plant is, Gordon was talking about defining your scope and your area of analysis. It was obviously quite easy for us because we had this whole pumping station that's supplying the mill. They had already online monitoring for the power that was being used in this plant, and it was very stable at around 2.2 megawatts. That's the high lift pump station. These are the original pumps that I think were installed in the 1960 sort of area. And then they had one newer pump, Sulzer pump, that's actually a 400 kilowatt motor, 6.6 kV. And that pump has got a much larger capacity than those other 4 pumps, individual pumps. So now you start seeing that there's an issue here. You've got one big pump, 4 different pumps in parallel to it. And then there's the line up to the mill where we were pumping. This is actually from the top of the clarifier. What data did we collect? We got 2 years of data, flow totals into and out of the plant. We had a whole lot of log sheets from the plant personnel that daily were recording, and it actually was very useful to get that data. We inputted that into a whole spreadsheet system, so you can analyze trends at different times of the year. How much water are they processing when the river turbidity changes? How does the river turbidity change? You've got these mental pictures of overnight it's shooting up, and then the next day it's fine, and all these sort of things. Flow totals into each unit. And we obviously, in the back of our mind, we're thinking about if we switch this plant off, can we now catch up once we've been off for 2 hours and supply the mill? One of the key parts of this project is you've got this plant reservoir that supplies the mill. So the whole idea is that if you can stop this plant, have you got enough storage capacity over there to keep supplying the mill while you stop the plant, and then you've got to catch up. So we've got flow totals for 2 years. We started looking at the power consumption of the entire plant. How does it change? Then you start getting more detailed individual power consumption of each of the pumps. Get all the pump curves, dig those out. Did a mass balance across the whole plant for different scenarios. When the water's dirty, how much water can you put through each of the processes? When the river water is clean, and then effectively it boils down to in summer, how much can you process in winter, and what's the average? So what did we find to summarize? Plant produces about 600 liters of clean water every second to supply the mill. On average, 30% of that water was returned to the river, irrespective of the time of the year. Baseline power consumption was 2.2 megawatts, and it was very constant, which was great from an MMV perspective, because now you're starting with something constant. The high lift pump station was a bottleneck, so if we wanted to stop the plant, we did not have enough pumping capacity to catch up in the 2 hours that we wanted to stop, and maybe even the 4 hours, because peak periods are from 7 to 10 in the morning and from 6 to 8 at night, when you're suddenly paying sort of double for your electricity. So it's very cost effective to stop a plant, if you can during those periods. The load shifting and energy savings were possible, and I'll go into that in more detail. One of the key sort of scary factors of this is if you're stopping this plant, how much can you process once you catch up, and what's the river plant turbidity doing? Now, the target of turbidity for the plant pumping out to the mill and to various other users was 10 NTU. The river water varied from 10,000 at the peak worst summer flood situation down to 3 in winter. So suddenly you see now, when you start looking at those trends, you say, well, in winter we've got a turbidity of 3 from the river. You literally don't even need the plant in winter. You can pump it straight up to the mill. That's how clean it's coming out of the river. The average was 540. So now you start getting a feeling for, well, you're actually operating in an average region far less than the scary 10,000 numbers that they're quoting to you. It gets more complicated, like all projects, when you start digging into it. The high lift pumps actually supplied quite a few consumers. After a while in the plant, we started talking, and I suddenly realized, well, wait a minute, where's the sealing water pump? Actually, the high lift pumps, which are supplying the mill at about 100 meter head to get up to the mill reservoir, were also supplying sealing water to all the pumps in the plant. So now they had 10 bar sealing water. First thing is that there's obviously an energy saving opportunity here, because you don't need 10 bar water for sealing. But also, if you switch off your high lift pumps and you're not switching off the rest of the plant, you've got no sealing water. They also used the high pressure, the 10 bar water on the from the high lift station for cleaning. So now if you switch off the high lift pump station, you've got no cleaning water. They also supplied the local municipality with 10 bar water. And when I say the local municipality, this is like a little water processing station that then pumped across the river, and it was situated about 5 meters above the plant next to it. So you've got 100 meter head water supplying a back pressure of half a bar. The final complication that caught me up right just before I was about to implement the project and get going was that I discovered that there was another small plant right next to the mill that was drawing off the line supplying the mill reservoir, and that was a separate production entity altogether. So if we stopped pumping into the mill reservoir, they wouldn't be getting any water, and I'd literally be bringing down another plant. And that was sort of mentioned to me as an afterthought right at the end. Oh, by the way, they're also drawing off the high lift line. So it gave me quite a fright. But now all of these situations, this project's a little bit more interesting than just purely energy efficiency, because now you're juggling load shifting and energy efficiency, and what you have to do here to enable load shifting is often also an energy efficiency opportunity. And it was actually quite complicated getting funding out of ESCOM, because differentiating what's load shifting and what's energy efficiency is quite tricky. We sort of predicted in future, if we were to upgrade the one high lift pump and install a new one in parallel to it, we could maybe get that down to 1 megawatt pumping power. The transfer pumps were also supplying this classic situation of pumping up to the A reservoir clarifier on the hill, 15 meters up, and the rest of the plants at the same level. So there was an opportunity there for energy savings. And then on the low lift pumps, there was some opportunity when, because they were overflowing and wasting water all the time. On the high lift pump station, we did a whole flow investigation and power survey, and then we modeled that whole high lift pump station. And I think I kept on going because I was just so amazed at how bad it was. And I couldn't really sort of believe the figures. So we confirmed the total flow versus power. We switched various pumps off and watched how the flow changed. And then typically in sort of any parallel situation, every time you switch on an extra pump, you get less and less gain for sort of a whole lot of extra power. And not surprisingly, the 4 old pumps were interacting negatively with the one big pump to a dramatic extent. And in fact, the last pump that they were switching on was doing something, but very little. And of course, those old pumps had different sized impellers in, and were throttled on the discharge to different extents. And because if they didn't throttle it, it would trip. So this was what we finally sort of went for. We modeled one new pump to match the existing big silver pump. Upgrade this one to be so that they're both the same size, 630 kilowatt motors instead of the existing 400 kilowatt motor. Control valves to control the mill reservoir level, because you can't be switching these things on and off too much. We're really going to be aiming it twice a day. And we're going to put a mill telemetry system to monitor the mill level. What they were previously doing is they were phoning up to the mill reservoir, and they would say, well, what's the level? And the guy would say, oh, well, I'm 95% now, so they'd switch one of the small pumps off. And a while later, they'd get a phone call and they'd switch another pump on, and they'd just play with switching the smaller pumps on and off. So on the high lift pumps, the existing pumps were sitting at about, we thought, 70% efficiency on the pumps 1 to 4. The bigger sort of efficient pump was sitting at a theoretical sort of 86% efficiency. So one of the questions that you've got to sort of juggle now as well, in theory, you can upgrade the smaller pumps and put bigger motors and do that whole analysis. Do you believe that they're going to be operating on their pump curves and that sort of stuff? And fortunately, it worked out that it was more cost effective to put in a new, more efficient pump, because I was very wary of believing the existing pumps that were so old would actually give me the performance that their curves were telling me that they would. On the transfer tank, I was talking about pumping to 2 different levels. In that situation, this is the original pumping sort of operating range. All I did on 2 of the pumps is I just trimmed the impellers, moved the operating range down to there, saving 60 to 80 kilowatts, and then I put 1 new pump in dedicated to the A reservoir, which is up on the hill. First thing, we put in a telemetry system to transmit the mill reservoir level down to the control system. Well, we actually completely upgraded their whole existing control system to put in a new SCADA system, so that one of the things they were scared of is that if you switch the plant off for 2 hours, then you come back online and something then goes wrong, as we'll typically do when you're starting up. Now you've lost, you haven't got so much reservoir level left to play with, and now you're waiting 2 hours to get an instrumentation die out and everything. So we put in a complete redundant SCADA control system, and we split the plant into streams so that if one analog card went out, then the other two lines sort of carried on running. So that was another sort of major change that we did in the plant. So we put, as I said, we upgraded one pump and one new pump in parallel to it. These two we kept as spare, and we demolished the two to get the new two pumps to get this new one in. We put in a small pump using that high suction head on the B reservoir to supply the local municipality. This B reservoir was one of the key things, as I mentioned. So our idea was that if we switched this plant, the high lift pump station off, and the river water was really dirty, we would continue to produce clean water into this B reservoir or buffer level. And so that the sediment, the water coming from here would go into the balancing tank, and then we actually would it's a bit counterintuitive, we'd actually pump from that reservoir up to the B reservoir, and then use that once we came back online, draw more quickly off that and pump and catch up. That guaranteed me. So the thing about this project is it's not it's guaranteed. It's the DSM process, so you actually have to guarantee what you say what you're going to do. So we guaranteed a 1.85 megawatt load shift, and we guaranteed 185 kilowatts energy saving, which changes the complexity of the project quite a lot. You have to be very, very sure about what you're doing, because if you don't achieve those guarantees, you're paying the penalties. So by doing that, I was sure at least that every single day I could stop this pumping the clean water for 2 hours and get sort of a 1.5 megawatt load shift as a minimum. And other days when the river water is clean, you can stop the whole plant and get up to 2.2 megawatts. Over and above that, if in winter, I feel that they should actually be shutting the plant down twice. But as you'll see, they're a little bit chicken. Then this issue that I mentioned right at the end, just before we implemented the project, someone said to me, oh, but there's another production plant drawing off the main mill reservoir. So what do we do about that? Now, the idea was, first of all, that they were struggling with their supply pressure, so I put in a very small booster pump to boost their supply pressure. It's like literally a 2.2 kilowatt pump. But when we stopped pumping here, I modified the piping system here so that we siphoned back off the mill reservoir to supply them, as opposed to pumping to them. Sounds like it should work, and the science said it should work, but the pipes, of course, go up above the reservoir, and there were leaks on them, and there were open air sort of nozzles and things. So I had to do quite a few modifications there, and it was probably one of the things I was most worried about with the siphon actually work. But after we put the pump in, I never ever heard a word from them again. So it seems to work. Then, as I mentioned here, we had to put in a high pressure cleaning pump so that if we stop these pumps, they can do high pressure cleaning. And we had to put in a dedicated sealing water pump, which was also an energy saving, because now they got sealing water at 3 bar instead of 10 bar. But it actually, from a payback perspective, it wasn't great from energy efficiency. We did proposed this project in 2006. And at that stage, the plant was saving around about 700,000 Rand a year. Now they're saving 2.2 million Rand a year. So the whole payback scale has changed now, but we proposed it to Eskom in 2006, and we got approved in the end of 2006. So the payback for all these modifications wasn't that great. It was really the load shift that was driving it, and Eskom was funding that 100%. What did we do on this section down here? We put in one new pump to supply that 15 meter back pressure or static head. We downgraded these two pumps, trimmed the impellers, and with one new pump. As you probably have noticed by now, we didn't put any variable speed drives onto this in this project, and it's, I guess, a bit what Gunnar was talking about. It's all a high. Generally, the major component of all your system curves is static head in this application, because you're pumping to a high head here, and up to the mill. Looking back at it now, if I were to do it again, with the cost of electricity being what it is now, that probably you could justify variable speed drives in some of the places. Like we could have put in a 630 kilowatt drive on the high lift pump station, but it's actually more cost effective for them to, and you would get a saving, but the other way to do it is for them to just stop pumping for longer. And then you catch it. So during the morning peak, when you stop for an hour, you've got a 3-hour morning peak. Instead of stopping for 2 hours, if you've got enough capacity, enough mill reservoir, you stop for 2.5 hours. And then you catch up at maximum rates and maximum efficiency. So I still think not putting drives in was probably the right thing for them. Because of this waste situation, they were always dumping at a constant rate from this centripetal grit chamber. So I put in a full ball valve into that line so that it didn't get blocked with all the slurry coming out, all the stones and stuff. And then I started controlling that waste water. And in winter we put it onto a pulse system where it only opens every few minutes. Whereas previously they would just have it sort of 30% open. And it was a knife gate valve, so they was worried about it blocking. And we put these control valves on here. That had two reasons for that. These pumps are drawing up from the river, so now when you stop this whole plant, you've obviously lost your prime on those pumps. So now you have to reprime them, and it was a very manual process before. They had little Nash vacuum pumps, they're priming the pumps, so we came up with a whole sort of automated system of detecting when they're primed and on-off valves so that you can prime each pump individually and detect when the pumps are primed. So that was another whole complication to switching this plant off. They very rarely have previously had to go and prime them because they were just running all the time. So these valves also had an added function in addition to controlling that level now instead of just overflowing it like they were previously. When the pumps stop, those valves close and you don't drain all this water out back into the river and lose more of a prime than you need to. And then if you start up, sometimes they actually literally open those valves to back flush it and speed up the priming process. So that's part of the PNID where we've automated that and put the control valves in and a flow switch to detect when the pumps are primed. This is the turbidity profile. I looked at this graph many times when I was struggling to sleep. You can see how the turbidity changes. They're talking there about 10,000 NTU, and that's the sort of nightmare scenario. The plant can't run, it struggles to keep up. But actually 10,000 NTU only occurred for very short periods, and then it drops down dramatically. And look at this period here. For that whole period there, you can virtually pump from the river directly up to the mill. So just broadly looking at the project, you can think, well, if they can keep up with the mill over there, and they don't literally bring the mill down, they're just struggling to maintain it, then you should be able to, for most of the time, switch off for 2 hours and catch up. That's the broad logic without doing all the detailed calculations which we did. So what was the scope of work for load shifting? We upgraded one of the high lift pumps to almost a full-size impeller, and put a 630 kilowatt motor on it. We replaced two of the existing high lift pumps with one big pump, as I said. We installed a new pump to supply the B reservoir, 132 kilowatt pump, a new high pressure cleaning pump, 110 kilowatts, new production supply pump, that was the small little one, that 2.2 kilowatts, but it was critical to the functioning of the whole project. New pump to the municipality, 22 kilowatts, level control system, that whole cyclone configuration, control valves, complete new automation system, an upgrade of the SCADA, the Siemens SCADA control system. On the energy efficiency side, we replaced one of the transfer pumps with a bigger 160 kilowatt pump, and we trimmed the impellers of the other two, and a new sealing water pump. Now a little bit more interesting bit, this is what the previous profile was of the plant. This is what we predicted we would do. Obviously it's straight because you're just doing a straight line for prediction. And this is what we actually achieved. These are the results after a couple of months. From the M&V results, so now when you're doing a proper DSM project, you get the university team to come and verify it. Gershwin actually was initially arguing with me about what's load shifting and energy efficiency at the beginning of the project, and then he handed it over to someone else. So these are the M&V results. We guaranteed 1.85 megawatts, and you're allowed to be within 10% of that. So the first set of results we got 97%, and energy efficiency we overachieved. And the second results we did better and better for the third results, and they've been running, even had just recently did another M&V set of results, and they were still fine. So what are the benefits? Load shifting during both peak periods. Load shifting is extremely cost effective for a plant, and I'm looking at some refrigeration projects now where they've got ice dams and things like that. Because your peak energy cost between 6 and 8, I think in winter, depending on your tariff, is about R1.50 to R1.80, and it's more than double what you're paying during normal periods. And even in summer, it's about double, but it's just a lower rate. So if you can move load from peak periods to off-peak periods, you can halve your costs. That's not even talking about the efficiency side of it, it's just when you're doing the work. So this project was basically, I think I've given the numbers soon, it was a 9 million rand project roughly. It's not a very big project considering some of the other ones I've worked on in pulp and paper, but it was funded the client only had to come up with about 2 million rand for the project, and they're getting now about a 2 million rand saving every year. There was a baseline reduction. That was one of the reasons Eskom also liked this project. When you do load shifting, you often create a new peak because you're pumping faster once you come back online. But as you could see from that profile, we dropped the overall load of the plant as well as doing load shifting, which created lots of arguments because they were saying, well, we were load clipping and things like that, but we got past that. So there were significant energy savings. Overall, if you just look at the difference between the two profiles, it was about a 25% energy saving. Just showing you some of the post-implementation programs. This is on the level control valves in the low lift pump station. That's the new transfer pump. That's the balancing tank before. That's after we put the 3 pumps in. That's the high lift pump station before. That's the new saucer pump that we put in. Financial benefits, total project value 8.5 million rand. Client cost 2.2 million rand. So they got a massive investment into their plant. And yearly savings, they're doing 2.2 now. Original payback when we started the project was 1.1 years for them. The other interesting thing about DSM is that you're getting the clients, in most of our projects, as you're implementing a series of changes in the client's plant, production plant, they're getting savings as you're implementing, and then they start paying you back. So actually the effective payback is often a lot better than that 1.1 years because they hadn't spent that money yet. Eskom was funding the project and the client's paying us some sort of progress payments as we're going. So once we've implemented something, then they start paying some more, and so the effective payback was actually less than 1 year. So in summary, we thought we were going to change 1 pump. We ended up installing 7 new pumps, piping, control systems. We load shift the entire plant, baseline reduction and load shifting, load shedding without a new peak. And that's about it. Thank you very much.